Ajit Redindran for welcoming the gathering.
Good evening, all. Am I audible? Veena? Hello?
Yes, sir. You are audible, sir.
Okay. Good evening, all. Uh, I am extremely happy to be a part of this webinar, which is the second one organized after the starting of IEEE Kerala SFES chapter. And even though we are in our budding stage, we could mark our own existence with a lot of activities planned, and we are driven by some eminent personalities who are standing as the backbone of this SFES chapter. First of all, let me welcome our chief guest, Mr. Venkatesh Prasad, Director, Nanochip Solutions Private Limited, and founder CEO, RV Skills and Industry Mitra, Bangalore. I would also welcome Mr. A.S. Varun Gaikwad, Regional Manager, Nanochip Solutions, and he is in charge of Synopsys VLSI TCAD University Program of South India. I welcome both of you to this webinar.
Thank you so much, sir. It's an honor to be here.
Okay, sir. Hope this lecture will enlighten all of us by knowing the recent trends in VLSI. Next, I would like to welcome the backbone of our society, Professor Muhammad Qasim S., who is the founder chair of SFES Kerala chapter as well as the vice chair of IEEE Kerala section to this meeting. Welcome, sir. I also welcome Dr. Ayub Khan GE, vice chair, SFES Kerala chapter, and Mr. Kader AA, secretary, IEEE Kerala chapter, and all the EXICO members of SFES chapter, who all are the guiding forces of this chapter to this meeting. Next, I would like to welcome all the participants who have joined in this meeting. Let us all listen to this wonderful session and get ourselves enlightened with the recent trends in VLSI. Thank you.
Thank you, sir. I cordially welcome each one of you to the webinar on VLSI and its future opportunities organized by IEEE SSCS Kerala chapter. We have with us two eminent speakers, Mr. Venkatesh Prasad and Mr. A.S. Varun Gaikwad from Nanochip Solutions. Thank you so much for sparing your valuable time for us, and I extend a warm welcome to you, sirs. Mr. Venkatesh Prasad is working as Director at Nanochip Solutions Private Limited and the founder CEO of RV Skills and Industry Mitra. He has over 30 plus years of experience in the electronics industries. We look forward to hear from you, sir. Over to you.
Okay, can you guys hear me?
Yes, sir.
Okay, so I'm going to just share my screen and we'll get started. Please tell me if you can see the screen. Is the screen visible, sir?
Yes, sir. Visible, sir.
Okay, wonderful. Very good evening to everybody, and I thank the organizers for inviting me here today for the second webinar of IEEE Kerala chapter. I'm especially excited to be talking about today's topic because this is something which is very dear to my heart. VLSI is one area where there are so many opportunities, but yet the brightest of the talent don't choose to, pursue a career in this area. And my job today will be to give an overview of what the landscape in VLSI is all about, what kind of job roles exist, what is it that the industry expects from students, and also we will go over some typical things about why is VLSI so important, what types of industries exist, and so on and so forth. So with that, let's get started. I, I have drawn from a presentation which I made to students at RV Skills, and I've modified it for this particular event. So the target audience is somebody who's really looking for jobs in the VLSI, and especially jobs in RTL design verification, synthesis, static timing analysis, physical design, analog full custom design, and so forth. Now, during the course of this presentation, you'll get to know what all this means. But for now, let's stick on with me. And in the process, if anybody has any question, I would encourage you to stop and ask your question so that I'll be more than happy to clarify that for you. I'll be spending about 20, 25 minutes on this topic, and then we'll talk about Industry Mitra and and how what kind of a platform we have created to get the industry and the academia closer together. So, especially for VLSI, people who come from one of these branches, ENC, EEE, uh, electrical and instrumentation, and VLSI teams can apply for jobs in VLSI. And prerequisite mostly would be knowledge of logic design and understanding of the analog full custom flow or the semiconductor physics, IC fabrication basics, and so on and so forth. So if you have this basic knowledge, you qualify to apply for jobs in the VLSI industry. Now, what is it that what specific opportunities exist? We will look at that shortly as time progresses. Now, before I get started, I want to put things in perspective. I always start my presentation and say that we began in a very humble way. And here is the picture of the first integrated circuit, which was attempted by one gentleman, Jack Kilby. Jack Kilby was a design engineer at Texas Instruments, and he conceived the idea of integrating discrete components onto one common substrate, and hence the name integrated circuit, right? So all the components are integrated on a common substrate, and there are many advantages of doing that, which we'll talk about later when we compare the PCB flow with the IC flow. Now, before we proceed, everybody talks about nanometer, micrometer, FinFET, so on and so forth. It's a little difficult to comprehend how small these things are. So I thought one way to, put things in perspective is to compare one single strand of a human hair, which is usually of a diameter of 30 to 50 microns, with the feature size of a transistor. Today we are at 3 nanometer, not even 35 nanometers. So 0.0001 micron is 1 nanometer.
Sir,
And
sir,
3
sorry.
micron.
Hello, sir. Sorry to interfere you.
Yes, sir.
Sir, can you make that screen in PPT mode, presentation mode? Actually, we cannot see the slide changing.
Oh, okay.
Thank
Uh,
you.
Let me see if I can share my, I will share my desktop, then probably that way I can see it. One second.
Okay. Yeah.
Is it better now, sir?
Yes, sir. Yes, sir.
Okay.
Fine.
So let me just quickly go back so that you don't miss anything. Uh, so this presentation is for people who are looking for jobs in the VLSI industry. And there are many specific job roles in the VLSI industry. One is RTL design and verification, logic synthesis, static timing analysis, physical design and verification, analog full custom. What all this is, we'll get to know in a few minutes as we get deeper into the presentation. Um, People from an ENC background, electrical background, electrical and instrumentation background can apply for jobs in VLSI. The prerequisite knowledge, the bare minimum knowledge industries would require is logic design, and unlock full custom transistor theory, network analysis. That kind of knowledge is what they're looking for. Now, we started in a very humble way, and here is a picture of the first integrated circuit, which was conceived and attempted by one gentleman by name Jack Kilby. Jack Kilby was a senior designer at Texas Instruments way back in the mid 50s, I think. He thought of the idea of having a common substrate with multiple devices on it, and hence the name integrated circuit. Now, to understand where we are today compared to the original, integrated circuit, we keep talking about micrometer and nanometer. So I'd like to bring in some perspective and to show people that what kind of complexities and the scale that we're looking at. Shown here on the left-hand side is the, if I were to take one strand of a human hair, which is typically 30 to 50, micrometers in diameter. Compare that with one single device. Today we are at 3 nanometers and 4 nanometers, and 1 nanometer is 0.0001 micron. So it's incredibly small, and you can see a transistor with your naked eye. And within a very small real estate area, you can fit billions of transistors on a speck, on a grain of a silicon wafer, right? So I just wanted to bring in that. So that is the reason why every generation the size of electronic devices is coming down, and it is becoming more powerful because transistors are becoming extremely powerful, and we can put a lot more transistors in a given real estate area, and hence we can achieve a lot of beautiful functions as time progresses. um, just to give you one more perspective is, today we are looking at chips which are before, the size of an IC was in 1 or 2 millimeters. Now we are looking at 11 millimeters by 8 millimeters, 10 millimeters by almost 7.8 millimeters. We use 8 levels of metal to achieve all the connections between the devices, 6 levels of metal, and now we go to 12, 26, 32 levels of metal. That's how complicated chips have become today. And when I say VLSI, I mean very large scale integration. So a lot of transistors can be integrated at a very large scale on a small substrate. And what you're looking here are some of the chips that I worked on in my previous companies um, uh, while I was in the US. Look at, here is another chip where you have 15 million and 18 million devices on the chip. So you're looking at a lot of transistors. And when you have to design something which has a lot of transistors, the way we think, the way we approach the design problem is very different. And we will talk about that a little later in the presentation today. So one of the key factors is, why do people even do business, right? So something has to drive the industry. So an industry will survive or it will be there only if it can address the customer. So the customer is the king, right? So what did the customer want? Maybe 40, 50 years ago, right? If you look at it 50 years ago, personal computers were fancy, like everybody were, wowed by a computer. People went and bought a computer home. And if you look at the industry at that time, all the IC industries at that time, every industry, including Intel, which was the father of this, which fueled the personal computing era, and every other VLSI company started, designing chips which was, meant for a personal computer. Fast forward a couple more decades, and you see the internet, came into prominence, and everybody started changing the design focus, and they started designing chips which was fueling the requirement for the internet era. Fast forward a couple more, 5, 10 years, and came the mobile phones, and everybody started doing chips for the mobile industry. New companies came into existence like Qualcomm, which got into developing chips for the mobile era. And likewise, as technology progressed, IoT came into picture, apps are becoming very powerful, big data and AI has come into the picture. And today, as we are speaking, we are in this phase where every company is putting out chips which addresses the mobile, the IoT, or the big data and AI analytics, right? So if you go look for job opportunities, you will see chips are being developed and designed for one of these requirements, that I've listed over here. Now, because the topic is about job opportunities in the VLSI industry, I thought it is important for me to explain how the organization of a typical industry is set up, and where a student will begin his career, and what is expected out of him, and what is or her career progression within the company is, right? So typically a company is managed by a chief executive officer or a managing director. Under him, sales, marketing, finance, technology, legal, HR, engineering usually report. And each engineering is further divided into business units. Only personal computing, FPGAs, set-top boxes, things like that. And each of the business units is headed by a VP, who in turn has managers, and managers would be specialists in either front end or back end, and below them would be an engineer who starts his job. So I'm assuming that predominantly the audience for today's session is new college graduates who are still in pursuing their engineering. So this is where they would start their career, and they'll have to work their way up to get to the management position. Now, having said that, I just want to pause for a minute. And hello.
Sunday.
Okay, I think there is some disturbance, so I'll continue. So I would like to pause for a minute and encourage everybody to think if they know how many types of VLSI companies are there today in India and throughout the world, right? So something to think about. Um, if if possible, can some of you unmute yourself and give me the name of at least one or two VLSI companies? Anybody that you know of, a VLSI company that you know of?
Wipro VLS, I think Wipro is having a VLSI division.
Yes, Wipro has a VLSI division.
And in
Very
Kerala,
good.
we have one engineering technology in
Okay,
industry.
excellent. Anybody else?
Radio.
DRDO, okay. Anybody else? I'm sorry?
Hello.
Yeah.
Hello. Hello.
Yes, please go ahead.
Intel, Samsung, sir.
Intel, Samsung, excellent. Okay, so you guys pretty much know what I'm talking about. Excellent. Okay. Now let's look at it at the next level of detail, right? So the types of VLSI companies can be listed as public and private. Private companies are those which have not yet gone public. They're not listed in the stock exchange. They have a private ownership. Whereas companies like Intel and Samsung, these are public companies. They're listed on the Nasdaq stock exchange, and they're answerable to the shareholders of their companies. Usually, public and private companies work on a very tight schedule, and time is king. So they have to deliver the product within a given amount of time. And also, they have to produce shareholder value. So they strive to work fast, cheap, and put out a better product, right? So companies can be classified as public and private. DRDO, I would say, is a government-owned public company owned by the government, not from a shareholder perspective, but it is a private government entity. There are tons of startups here in Bangalore, at least, which are private, which have not yet gone public. Another way to look at a company is we could have a EDA company which serves the VLSI market. You could have a fab which serves the VLSI market. You could have a service company which serves the VLSI market. And you could have product companies which serve VLSI markets, right? So all of these are VLSI companies. So an example of a EDA company is companies like Mentor Graphics, Synopsys, Cadence. These are companies which provide electronic design automation software, which is used for the design of VLSI chips. Likewise, there are fabs which help in fabricating a VLSI design. And today, most of the companies are fabless companies. They don't own a fab of their own. They go get into an arrangement with a fab, get the fab models and the fab process technology, understand it, and use that to design their chips. And that is called as the fabless approach. So examples of some famous fabs that are there in the world today are Global Foundries, TSMC, Taiwan Semiconductor Manufacturing Company, UMC, United Microelectronics Corporation, CSM, Chartered Semiconductors, Hynix, IBM, so on and so forth. Intel has a fab of their own, but they use it only for their products. It is not for public consumption. Likewise, there are service companies, and Sir talked about Wipro. Has a VLSI wing where they don't produce a product or they don't design a product, but they augment staff in all these other companies which have a requirement for skilled qualified engineers who can work and produce a product. So Wipro Tata Elxsi, TCS. These are companies, which are in the services sector of VLSI. And the last or the second last is product companies. So if I look at examples of product companies, Samsung is a product company, Intel is a product company, Qualcomm is a product company, NXP is a product company. Like that, you have many companies which have a chip to their name, and they take engineers, take the help of the fab, take the help of service companies, take the help of VDA companies, and together put out a product into the marketplace. Now, what kind of companies, product companies are there? We could have product companies which design ASICs, FPGAs, or develop only IPs. So, for example, an IP company which you all might know is ARM. ARM puts out processors, the ARM 7, ARM 9, ARM 11, ARM, RISC processors, which are used as intellectual property by these product companies, and they integrate the ARM processor into the chip and go to production, right? So the advantage obviously is they can get to market quickly because the design would have been done quickly. Again, you can classify companies as analog companies and digital companies. So if I look at Texas Instruments today, Texas is a public product analog company because they're predominantly very strong in analog design. So when you look at VLSI job openings, it would serve you well if you're able to mentally map the company, what is it? Because once you understand what the company does, it will help you be better prepared from a resume perspective and also for your interviews so that you can understand how to position yourself for your advantage in getting a job in these companies. So the learning from today's exercise should be that there are 5 different types of VLSI companies: EDA, Fab, Service, Product, and IP companies. And each of them, though are VLSI companies, the requirements and the expectations are slightly different. And understanding what they are will help you, from your career planning. The way things are going or progressing in the industry today is integration, right? What were 3 chips, just a few, years ago is all integrated into one big chip, and that is called as and hence you get what is called as system on a chip kind of a situation. So a single chip by itself can act as a complete system. It has memories, it has processors, it has controllers, it adheres to multiple protocols. Just with a single chip you can build a complete system, so hence the name system on a chip. Now, before I proceed further with an IC thing, since everybody would have some knowledge of a PCB, let me quickly give you an overview of what is the difference between a PCB and an IC, right? So if I look, PCB, they're bulky, whereas integrated circuits are small, and the integrated circuits can have lots of transistors on them. PCBs are made from discrete components. So I don't manufacture any of the components. I just mount them, solder them, and draw the connections between them. So they're made using discrete components. But inside an integrated circuit, the discrete components are also fabricated, and all of them are fabricated at almost the same time. So all the active and passive devices are inside the IC and they are fabricated. In a PCB, we're talking from a millimeter scale, whereas in an IC, we're talking the nanometer scale. In a PCB, we can accommodate large resistors, capacitors, and inductors, and thereby we can handle large voltage and currents. Whereas in an integrated circuit, we cannot accommodate very large resistors, capacitors, and inductors because it is not good value for money. It is better off keeping them as discrete components outside. That's why you see in most PCBs, you have multiple ICs, but at the same time, you do have resistors, capacitors, and inductors off the IC on the PCB because it's not very area efficient to have such large passives inside ICs. PCBs, we can handle large values of currents and voltages, whereas in integrated circuit, we cannot do that. The maximum we can handle is perhaps in the high microamp range and maybe 1 or 2, maximum 3 volts, because at very, very small geometries, the electric fields will become so large that, even though we are operating at 1 volt, then the electric field across the gate oxide can be so large that it can destroy the gate oxide if the voltages exceed a particular threshold. So that's why integrated circuits, at least in the deep submicron process nodes all operate at low voltages. Now, let's look at what an ASIC is. Briefly looked at what a PCB is and what an integrated circuit is. And there are many types of integrated circuits, and let us see what they are. Before that, I have to understand what an ASIC is. An ASIC is an application-specific integrated circuit. In short, it is an ASIC and is used to design, chips of a specific nature. So there are two types of them. One is general purpose. The other one is, application specific. So what I'm showing over here is video processor, audio processors, low power DSP controllers. These are all specific ASICs performing a specific role. You also have general purpose ASICs like op amps and so on and so forth, which you are used to from the college days. An ASIC can be further classified as full custom, programmable, and semi-custom. So if you look at a full custom ASIC, as the name suggests, I can use this full custom approach to design analog circuits, as my main this thing. Likewise, if I have to design, if I have a very low quantity but I have to get to market quickly, I use what's called as an FPGA design flow. And if the volume is large and I have time, I use what is called as the ASIC design flow. So in the next few minutes, we will look at these two flows in the next level of detail. And from there, we'll figure out what are the various job opportunities as a full custom engineer and as a semi-custom engineer, and see how you can position yourself for jobs in the VLSI industry. So you have heard about this SSI, MSI, LSI, and VLSI. Just for completeness, I've put this over here. We started with electron tubes in the 30s, then vacuum tubes, then transistors, discrete components, and Jack Kilby came about with this integrated circuit, and that is when things started going forward, and there was no looking back. Flip flops, NAND gates, OR gates, all fall into this SSI category. And if the circuit is small, I can use the traditional approach of designing, which is the full custom approach, which we'll talk about in a minute. If the circuits become big, like VLSI and ultra large scale integration chips like the SoCs, I can't use a circuit design approach. I have to use a slightly different approach called RTL design, which we will also talk about shortly. So in the analog design flow, transistors are the building blocks. They are the primitives, and the layouts are drawn manually. Everybody knows this. In your college, you've studied about an RC coupled amplifier, perhaps, or a power amplifier, or a class AB amplifier, and stuff like that, where you draw the transistor circuit. Right? So I also use the analog flow to design standard cells and macro cells, which are used as building blocks inside the ASICs. And the analog flow is perhaps the most, gives you the highest performance, but since it is all done manually, it takes a very long time to design an analog chip, right? So hence, this kind of a flow is not suitable for very large count, high transistor count designs. So let's look at what is a flow, right? A flow is a sequence of steps that you have to follow such that you can get the end product quickly. So if you're building a house, if I were to look at what is the flow that I follow in building a house, I first gather specifications, then I design according to the specification and verify my design with the client, run some simulations, use AutoCAD software, and so on and so forth. And once my design is frozen, then I implement the design by getting in touch with the civil contractor. He will get the bricks, the cement, which is the IP, which I use to build my house. And once the house is built, they engage with an interior designer who will finish off the painting, woodwork, carpentry, so on and so forth. So you see, to build a house, I need people of different job roles, right? So you need the architect. He's specialized in coming up with the design by reading the specification. I need somebody who can vet this, a structural engineer, so on and so forth. Then need somebody who can implement this like a civil contractor, and so on and so forth. Then an interior designer. An interior designer cannot do the job of the architect, and an architect will not do the job of the interior designer. But together, in working in a sequence, they can build a house. Similarly, in IC design, we have specialists at various stages of the design flow, and they have to work in a team to make sure the chip can be designed to meet the specification and also in the shortest possible time. So now let's quickly look at the analog design flow. So in the analog design flow, let's say I'm designing an inverter. I start with the design spec, and the spec for an inverter usually is if the input is 0, output should be 1, so y is equal to a bar. And also it has what is called as a timing spec. So it should invert within a given period of time called as a propagation delay for a given voltage, right? So we start with the design spec. From the design spec, we get to what's called as the architecture of the design. So you can say that one PMOS and one NMOS will make an inverter. Then I design that circuit. So from the architecture, depending upon the voltage and the propagation delay, I decide what is the length and width of the transistor that I can use to achieve the required propagation delay. In order to do that, I run what is called as a SPICE simulation, where we get the SPICE models from the fab where the inverter will finally be fabricated. And from there, if it meets the specification, I go to the next step, which is called as the layout design. Here the circuit's layout is drawn manually, transistor by transistor, and I have to verify it by running what is called as DRC and LBS, and then do parasitic extraction, post layout simulation, and if it meets all the specifications, then I send it to the fabrication for fabrication. So if I look at this design flow, there are multiple steps over here. So I can classify two job roles over here. The first job role is backend full custom analog layout or backend engineer. The next job role is full custom or analog circuit front end design engineer. So usually the job of a front end designer is to design the circuit, and the job of a backend engineer is to draw the layout of the circuit. So if anybody over here is interested in jobs as analog circuit designer, you must have very strong knowledge of network analysis. You must understand semiconductor device physics really well, and you must be generally good with mathematics and transient circuits, RC networks, so on and so forth, right? Because your job will be to use physics to pick the kind of device and its characteristics, which will get your job done for you. And this analog design flow is used to design small digital circuits, small analog circuits like op amps, comparators, ADCs, DACs, low pass filters, low noise amplifiers, and so on and so forth. As a backend design engineer, your job will be to draw the layout of a circuit and verify that layout to meet the manufacturability requirements like DRC and LVS, run a parasitic extraction, and then finally send the design to the fab. A layout engineer is expected to work with a circuit designer because the circuit comes from the circuit designer and goes to the layout engineer. They both have to interact back and forth. So it is expected that the layout engineer also understands some amount of device physics, understands how to read a circuit. So if he sees a circuit, he must be able to say whether it is an inverter or an analog circuit or a digital circuit, whether it is an op amp or things like that. So he must be able to quickly identify the functionality of the circuit. He need not know how the circuit works, but by looking at the circuit, he must be able to say what kind of a circuit it is. So I spoke earlier and said, many chips are made into one single chip, and that's called as an SoC. That's what I'm trying to show over here. So looking at a size of a chip which has billions of transistors, obviously I cannot use the method that I used to design analog circuits. So I cannot use transistors as the building block. I have to think of another way of designing the circuits, and that's what we're going to talk about today, right? So in an ASIC, by definition, ASICs are big, design specs are complicated, it has many features. So we start with the spec, then we do what's called as RTL design. From the RTL design, I get an RTL code. That RTL code is verified using a system Verilog and UVM and stuff like that. That is synthesized, and when I synthesize, I get the circuit in the form of gates. Now that is sent to another tool called as a place and route tool, where we do what is called as automatic place and route, generate the layout, and that is sent to the fab for manufacturing the chips. So what I've shown over here is a very, very high level description of the design flow, and there are multiple job roles over here as a design engineer. So RTL designer, doing the design itself is one job. Verifying the design itself is one job. Synthesizing the design itself is a job role. And doing the layout of an ASIC is itself a different job role called as the PD flow. You call them as physical design engineers. So in the next slide, I've further broken them what happens in each of these subflows over here. So there is one is called as design, verification, synthesis, and physical design. So this job is for people who are looking for RTL design engineers. So if you want to be a good RTL designer, you must be good with HDL languages such as Verilog. So if you understand Verilog, if you know how to translate a requirement into an algorithm, and from that algorithm write the code, then there are a lot of job openings in this field for RTL design engineers. All A6, the entry point is RTL design. So you can, after this session today, I would encourage each one of you to go online and do your own search. Look for job openings for RTL design engineers, and you will see tons of job openings from Intel, Qualcomm, Wipro, TCS, small startups, and so on and so forth, where they are looking for RTL design engineers. Of course, there are many specializations over here. You do low power RTL design. You use what is called as a UPF, Unified Power Methodology flow for designing the chip. The scope of today's discussion is not to get into each of this. So I'm just giving you an overview of what the whole thing is all about. Once the RTL design is done, you do what is called as RTL verification. And here the design has to be verified. 60% of the job openings exist in RTL verification. So in order to be a good verification engineer, you must understand two languages called a system Verilog and UVM. These are verification languages which are used by the industry today, and you can look up on the internet job openings or scope for RTL verification engineers. Tremendous amount of scope. And at RV Skills, we every year we have a shortage of people to be placed with this expertise over here. So if you're the person who likes programming, C, C++, OOPS, and stuff like that, you will find RTL verification very easy for you. But if you hate programming, please don't even consider RTL design and RTL verification jobs, because these are all requirement here is you should know programming. And if you know C, that, and if you like C, that means you like programming, and you can consider looking for job roles in design and verification. Once the design is verified, the last stage is where you synthesize it and you do a physical design for it. This role requires people to be strong in logic design. You've got to be good with programming, like Tickle and Perl scripting. You have to know how to use software tools much more better than the here. Software tools are not that important, but here understanding the use of Synopsys Design Compiler, ICC2, Prime Time, stuff like that, Hercules, IC Verify. These are tools which are used for design verification of the layout. So knowledge of the layout will become extremely important in these cases. You should be good with logic design. You should be good with understanding how circuits work under different conditions, under different PBT corners. You should know a little bit about the fabrication process. You should know what in the layout of a design will mess up the timing. So what are delays in the layout? So you should know RC circuits and so on and so forth. So if you feel that that's where your strength is, then you should consider jobs in this area. But um, as we are talking today, there was a semicon conference which happened last month, and the Minister of Skill Development Rajiv Chandrasekhar ji personally was there for all 3 days in the conference, which is a rare thing. And the government is out there saying that there is an acute shortage of manpower, and they have taken up the task of skilling 85,000 engineers in VLSI design across all these various domains. So um, the requirement is real, the need is real, and it is immediate. And once you become a VLSI engineer, and if you really choose your career choice wisely, there is no looking back. We have trained about 10,000 engineers in the last 17, 18 years. And I can tell you from my personal experience that, getting 70, 80 lakh rupees salaries, if you're good, is not rare. A lot of my students are in that, pay bracket, and they come to the institute to hire people. And, we are very happy to have helped people from throughout the country, come get trained and get skilled in this area. So the need is real. There is a lot of competition because this is not everybody's cup of tea. But if you keep your ears and eyes open, put a little bit of hard work right from the first and second semester, it should be achievable to become a professional in the VLSI industry. And most people 5-10 years experience over here. The next destination is US, Europe, or you know, um, or Australia, or to London, and they get handsome pays out there as VLSA professionals. So we spoke about all this. We looked at all the various opportunities. The most important thing is how should you train yourself to get these skills. And here are some things. This is my view, personal view, which I thought I should share with you. This is the approach one should follow, especially to gain skills, because you are looking for skills. You're not looking for knowledge. So skills means you should be able to apply the knowledge, use software, make mistakes, and design is an iterative process. You should converge to getting the design right. And this is not that you either know how to design or you don't know how to design. All designs to begin with, you'll have some idea. You won't know what the final design looks like, but you should have an approach in place to get there. And that's why software and simulation tools and things like that are used. So the approach that I would highly recommend, if you are interested in acquiring skills, not knowledges, you first listen to your lecturers, right? So they teach. This is followed in all academic institutions by way of lectures, very much needed. This forms the foundation, or 20 to 30% of your knowledge you get from teaching. The second is, watch tool demos, pay attention to the labs that happen in your colleges, because that is where you are shown how to use the concepts that were taught to you in the class and learn. So here you learn another 20 to 30% of the things, and then you watch, engage with a guide. You have to actually start working on something, and this is where you'll make a lot of mistakes, and that's okay. Your guide should be able to guide you by watching you make those mistakes. So here is your chance to learn differently. We have this component AICT recommends as part of the project, where you're supposed to do your projects and your guide is supposed to guide you when you make a mistake. A lot of people don't take that seriously, but in my view, that is the most important aspect of acquiring skills. Please use that wisely so that you can get what you want. And finally, if possible, engage with somebody from the industry who can give you that perspective of how to learn and how to learn on your own, because that is extremely critical. The whole point over here is, I want to say is, your aim should be to work for a manager and not for a teacher. Because when you go to work in the industry, you will report to a manager, not to a teacher. And a manager is a very lousy teacher. He might know his concepts really well, but he might not know how to teach to you. Teaching is a very specialized profession, and teachers know how to put across their ideas to you in a manner where you can understand. So you cannot use a strategy of going to the industry and expecting your manager to teach you, because that is a failed strategy. So you should become manager ready. So a manager expects you to learn on your own. And when you follow this approach to learning, you will find this very comfortable. So when you go to the industry, you might not know things, but that is great. But your manager will give you some tips and pointers as a coach, and you should be able to pick things up from there and proceed forward. And that is the methodology I've been following from the last 18 years. And 10,000 students have been trained this way. And we are seeing tremendous results, and a lot of people are getting jobs. The placements is 100%, and every batch I have a shortage of people to place in the VLSI industry. So I would suggest that you people follow this. And lastly, this is something which I felt over the years we have to give some attention to this, and that is professionalism at work. So if you see what the industry is looking for, industry is definitely looking for people who have knowledge, definitely looking for people who have skills, but at the same time, our behavior also matters. Coming to office on time, making sure that you're accountable, using resources wisely, not engaging in gossip, politics, so on and so forth. So professionalism is extremely important, and if you have this, you will get the job. Otherwise, no matter how smart you are over here, it will be a challenge to get jobs in the industry. English is also one thing which I find is a challenge. So you have to be very cautious when you're speaking in English, because our mother tongue is not English. So we think in our mother tongue and express in English. There might be a communication gap which could cause complications and so on and so forth. So watch out what you get from the internet. There are a lot of limitations. Only knowledge and skill will get you a job, will not get you a job. Your attitude and your behavior will get you a job. With this, I'd like to play a small sound bite and then I'll end my presentation over here.
To be successful in corporate career, you need three key aspects. One is knowledge, second is skills, third is attitude. Together, these three constitute what we call as a triangle of success. Now, knowledge is about what you learned in your schools and college, reading books, interacting with the people. So it could be technical knowledge or common sense. Knowledge per se is not enough unless you practice it. You put it in practice. You would have done a project, you have done internship. During this time, whatever you have learned, you have applied it to create a new product or new module. So during this process of doing things, you develop skills. So the skills could be goal setting, time management, reasoning, communication, interpersonal. They could be technical or people skills. Apart from knowledge and skills, you need to have a positive attitude. Attitude is about how do you take life, whether you are a positive person or a negative person. If you are a positive person, you deal with problems with self-confidence, you're motivated to work on things, you have integrity and honesty, you have optimism and enthusiasm, and you like to cooperate with other people, and whenever you do commitments, you try to honor them. So when you have all these three aspects, you are likely to be successful in career. Many times we talk about competency. What is competency? It is summation of knowledge, skill, attitude, and also the behavior. How exactly you behave yourself in day-to-day life. When person has all these things, we call that person is very competent. Now let us take an example of a carpenter. When you will say a carpenter is very competent, obviously he should have the knowledge of carpentry. He should know how to do things. He should be experienced in carpentry, like doing furniture, sofa, whatever it is. He should have the right attitude. So he should be willing to learn new things. He wants to do a good job. And behavior. Actually, he does the work. It is not that he knows but keeps idle. It's not that. He actually day in and day out, he works and does things. So when we have all these characteristics in a carpenter, we can say he's a competent carpenter. Same is true for any career. Let us say you are a software engineer. When you have the knowledge, skill, attitude, and the right behavior, we can say you are a competent software engineer. Same is true for any other field.
All right, so that's all I had to present today. I hope this session was informative and you got something out of it, and it will help you, at least to start think about VLSI. I would like to reinforce the fact that there are lots of job openings in VLSI, handsomely paid, and this is one career where you get to a chance to apply what you have learned in your engineering. It is not for everybody, but if you're able to master this, it's an extremely challenging, interesting, and highly rewarding career. So with this, I would like to end my presentation. If there are any questions, I'll be more than happy to take them and answer them for you.
Hello.
Yes, sir.
Venki, what about the early skills training courses and industry method? A few words on that, Venki.
Yes, we will talk about that. Before that, if there are any questions that they have, I'll address that, and then quickly talk about industry.
Yes, since on the job opportunities, skilling also an important options, right?
Yes.
Yeah.
So any questions based on what we discussed so far, comments, questions? I'll be a little eager to know from the audience over here.
If any questions are there, they can share it to with their name, roll number, or college name. Share it to Ajit sir so that we can reply later also.
Sure. Okay. So what I'd like to conclude today's presentation is with a talk on Industry Mitra. My colleague Varun is not able to speak. He has ulcers in his mouth, and so he requested me to do this. So I'm doing this on his behalf. We have a new product called Industry Mitra, where we have a bunch of industry professionals on one side who have put together a platform with content which is proven, tested, and has all the features to make online learning fun and rewarding. And I'd like to quickly go over that today, for the benefit of the audience here. So Industry Mitra is a platform which is rich with content. It has a virtual lab integration, so you can actually, through the portal, get into the lab and pick a tool of your choice and run your simulations. It could be in C programming or Python or Java or cybersecurity. A host of courses, very rich with courses in there, and it is scalable, it is cost effective, and it is supported by industry veterans. And all the people who have contributed to this are people from the industry with decades of industry experience. So we can vouch for the authenticity and the relevance of the courses that are there on the platform. It can be used by schools and colleges, professional institutions, government bodies, universities, individual trainers who want to use this as a platform to deliver training to their students, B2C students, and also corporates. So it is easy to use, has a lab integration, consumes very low bandwidth, supports very large number of students at any given time. You could run live classes, you could run a blended learning program, you could do self-learning. It provides useful analytics about to the instructors, about the students, or to the students themselves. So for the courses, we have quizzes and things like that where we can see if you're strong on the concepts but you're weak on the application of concepts. How job ready are you? If today after the course is over, if you take my test, how likely will you get a job offer? If you don't, what are the areas you should improve? If you get, what is the career progression? What are the other course maps you should take so that you can become an expert in a specific area? So that like that. So we have what is called as career paths. So if your goal is to become a VLSI front-end engineer, we will tell you take logic design, take a course on VCS, take one course on Verilog, take a course on low power design flow. All these three put together will qualify you to become a design engineer. So you will know exactly, you're guided in the right step for every job role. We also have a lot of startup partners who are working with us and who are keen to get people from who are skilled to get absorbed for placements. We have an admin and a course authoring section and so on and so forth. Um, it's for if you're an instructor, it is very easy to put your content onto the platform or use our AI engine to build your own platform. You can use this in the instructor mode to run a class. You could also use it in the student mode for self-learning, assisted learning, interactive learning, and so on and so forth. It is mobile friendly. You can ask questions to the instructor while you're watching the video. You can bookmark a question, and the instructor will be notified that student A has a question at the 30th minute of the video on what you said. Please clarify in the next class. So the next class he can clarify those questions. And it is very rich and it is used very successfully in RV institutions at RV skills. Government of Karnataka is using it, and we're using it with a private university called Kalasilingam in Madurai. And so far, about 7,000-8,000 students have actively used this, and we're getting a lot of interest from others to take this platform, which is rich with content. So if anybody is interested, we'll be more than happy to work with you, schedule a demo, and show you how to use the program. And we also run a few diploma programs at RV Skills in the various job roles, as one for design engineer, one for verification engineer, one for VLSI, full physical design engineer, and full custom layout jobs. So we've covered most of the job roles which are in demand for placements. We continuously have an acute shortage of skilled manpower at any given time, at least ever since COVID opened up. You all might have heard about the semiconductor component shortage, fabs not being open, and Indian government is trying to set up a fab and things like that. We are, eagerly willing to, waiting to help people who are keen to get skilled to get into the VLSI industry. So this was a very quick overview of the Industry Mitra platform, which is rich with courses, assessment, and proctoring. We'll be more than happy to work with you, if you're more interested in this particular product. With this, I'd like to end my session, and I want to thank the organizers for giving me a chance to express my views and thoughts to you. And I hope that this was a useful session. And if there are any questions that you have, I'll be more than happy to address it for you guys.
Hello, sir.
Yes, sir.
Yeah, sir. Thank you for the wonderful presentation. And I have one small doubt.
Yes,
Actually,
sir.
yeah, recently I came to know that in VLSI, then that means in VLSI, the integration of AI is happening. So, what is the future of this job roles with the integration of this AI into this ICDC?
Okay. It's a very good question. Thank you for reminding me. I didn't touch upon that. They say one thing which is constant in VLSI is change. So when I started my career, we are looking at 5-micron technology, and now we're at 3-nanometer technology. So the way the chip is getting manufactured is becoming more and more complex. But the time that is there to design and fabricate the chip is still the same, right? So human beings have a limitation in processing data. So that is why AI comes into the picture. Certain aspects of the design flow, which is repetitive in nature, we don't need a human being, and we can use software tools which are smart enough, which will figure out how to do things in a better way. So, for example, if I'm doing the layout, if I incorporate AI principles into it and tell it this is how I want the layout within this much area, with this much parasitics, and with this much time, the layout will start doing things, the tool will start doing things automatically, iteratively, and you as an engineer are expected to see if the algorithms are heading the right way or not. So if at all knowledge of basics, understanding Python programming, understanding how the AI engine for some of these tools work will become very, very important. But the underlying basic concepts are still solid, intact, very much needed. If you don't know how a transistor works, but expect the tool to pick one and design it, then if the tool makes a mistake, you're in trouble, right? So AI works well when there is repetitive jobs that needs to be done, and the end goal is very well known and documented for us. So basics is still needed. Certain aspects of simulation is driven by AI. It will automatically figure out at what increments of the voltage it has to be swept, what should be the bandwidth that it has to calculate for. It will suggest what needs to be changed in the circuit in order to converge on the timing or on the power issues and so on and so forth. So the flow will still be the same, but the tools are becoming smart enough, and hence they say the tools are AI driven and AI compliant. I hope I addressed your query, sir.
Yes, sir. Got it. Sir, one more doubt from the student perspective, whether they need to have stick on some software or whether they need to give some importance on the software for getting into VLSI industry.
So there are two aspects. You definitely need to get your basics strong, and that is where the role of the college will come, because when you go for a job interview, there are two steps. One is a written test. The written test, always they check on the basic understanding of concepts, and once a student clears that, then when they go for the job interview, they expect people to know how to use the software, or do they have any experience having used the software, and stuff like that. So in the order of priority, concepts is very important. If they know that, if they don't know software, still okay. But it's a competitive world. So if everybody knows the concepts well, and there are 10 students who know the concepts and the software, obviously they are the people who are picked, up in the industry. So suggestion is focus on the basics, and there are are 4 or 5 subjects which is very critical for VLSI. Electronic circuits, network analysis, Verilog HDL programming, then semiconductor devices, network analysis. So if you understand these 5 subjects, you should be able to clear the written test quite comfortably. But once you've done that, people will say, did you do a VLSI project? If so, which software did you use? What challenges did you see? So that is when you get a chance to explain about the knowledge of the software that they have used.
Thank you, sir. Yeah, got it.
Yeah.
Hello.
Sir, one question from here. This is Pamela. Basically, when you touch upon the AI topic, can we, in a nutshell, say that AI is right now into the back-end design of VHD, all the VLSI flow, and front end is, of course, by still the expert engineers. I mean to say the design part we have to still do. The simulation tools are probably AI driven or the layout tools. So it
Yes.
is like a back-end tools that would be AI driven. So that's where a student has to concentrate if he or she has an AI knowledge.
Yes.
Can we
So,
say like
yeah, you're absolutely correct. And AI is predominantly, a function of the tools. Tools are smart enough today where what was an extremely iterative manual process, the tools can automatically figure out what should be the next iteration, what should it change, and run the simulations again. So, but your knowledge of AI is not that much required to an extent because there are no tool development jobs in VLSI here in India today, right? Even Synopsys, Mentor, or Cadence have their setups over here. They're not doing heavy coding of the tools over here. So the coding and the algorithms are still developed in their parent companies in the US, right? So understanding the basics of AI and how AI algorithms work and how to write some simple, wrappers in Python would be very useful for you. For example, Python programming is used in verification to automate the test suites. So we call that as regression testing. And what people have found is when they see a bug in the RTL design, a bug is reported by the verification engineer. The RTL designer fixes that bug but introduces a new bug, right? So the number of test cases export exponentially. So to manage these test cases, make sure you get good code coverage and functional coverage. You write Python programs which make life a little easy, and you use statistics to ensure that you got good coverage and so on and so forth. So you don't need to know deep, algorithms type DL, ML, and AI kind of a stuff. It would suffice to know that AI means a tool is working towards achieving the goal, and Python is something that is being used. Unless you're working seriously as a developer, developing EDA software which use some of the AI algorithms.
Yes, sir. Thank you. Like then students they need to take a message that a basic Python course with some statistical key performance indicators. In
Yes,
that way,
yes.
if they are familiar with that, that would be an advantageous to them.
Yes. Only that will not help though. But yeah, along with everything
Thank you.
else, they should know this.
Yeah. Thank you.
Sure.
Thanks, Ravindran sir, and all the participants. Please mail your queries to Ajit sir and Varun at nanochipsolutions.com. So that we would like to share your query, whatever your queries regarding the industry mitra or the RA skills, VLSI training, or the topic what Venki spoke about. We would like to answer your any of your queries or doubts or any information which is required, either through Ajit sir, and you can copy to me at Varun at nanochipsolutions.com. Okay. So thank you. Thanks, Ajit sir, for providing this platform for us to give a presentation on these VLSI opportunities.
There was one question from a student. He says he's from third year, and what should he do right now so that by the time he finishes his final year, he can get to the industry. I would highly recommend to maybe do a project in VLSI, or while in the third year, we have engagements with colleges where between the semester breaks we engage and we train them on specific topics just enough for them to clear written tests and face the job interview. I would suggest that he explores things like that. Definitely, if time permits and if it is possible, I would suggest that he does a course and skill development diploma course as part of his final year. A lot of students do that nowadays, by the way. A lot of students from Andhra and Telangana who seek our help in this manner. And during their final year, they come and do the project over here, submit it, and by the time the degrees are over, they have their job offers in hand. So I would recommend that if anybody is seriously considering how to be job ready by the time the engineering is over. Final year project is the time where you should get the most out of it. So if there are any other questions, I'll be more than happy to address it. Okay, so looks like
Yeah. Sir. Yes, sir. I think the queries are over. If I
yes.
got some mail, I will definitely forward to you and I will connect with them.
Sure, sir.
Yeah. Veena, please. Yeah. Sir, I think I think Veena is not connected.
Okay.
I think she is having some issue. Sir, can you please turn on your camera? We can have a small photo session and we can
Yes,
wind
sir.
up the session. Yeah.
I was afraid of that, but anyway, I'm ready for it. So I've turned on my camera.
All the participants, please turn on your camera. Thank you, sir.
You're welcome, sir.
Sir, shall we wind up?
Yes, sir. Yeah, I think I have some audio issue.
Okay.
Now I call upon our secretary, Khadar sir, to give the vote of thanks.
So, as part of our talks organized by the Solid State Circuit Society of Kerala, I thank from my heart Mr. Venkatesh Prasad, Director Nanochip Solutions, for his very wonderful explanation about the opportunities for the ASIC and VLSI uh, in the SIC and VLSI industry for the students. He described the methods for gaining skills in this competitive and exciting field. So what he said about teach, show, watch, coach was very inspiring. The methods to get skills in this field. So it's a very inspired. It was a very inspiring talk, sir, Venkatesh sir.
Thank you, sir.
And the way he explained about professionalism, how you combine the behavior, skills, and knowledge was very nice, and it can be easily applied. And he also explained the triangle of success, where attitude is everything, along with your skills and knowledge. So also he introduced Industry Mitra, which I got to know a few months back. And he also explained about the integration of AI with VLSI. Thank you, sir, for this wonderful talk. And we hope to hear from you in future also. Thank you, sir.
Definitely, sir.
And
Thank you for having me.
I would like to thank Mr. Varun Gaikwad also for attending this program. Thank you, Mr. Varun.
Thank you, sir. Thank you, Khaled, sir.
Yes. And thank you all participants for coming to this online program and attending this, and hope this has enlightened you to take up VLSI as a job for your present and future, and hope this will open your vistas to new areas of design. So as sir told about AI also, it's a very promising field. And thank you all my colleagues from IEEE, Ajit sir, uh, and I should also thank Kasim sir for his support, and all my colleagues. So thank you all.
Thank you, sir. Have a wonderful day, everybody.
Yeah. Thank you, sir. Thank you very much.
Thank you. Bye-bye.
Yeah.
Thank you, sir. Bye-bye.
So I think Veena had some audio issue, so she already announced. And please complete the feedback form which is shared in the chat box for getting the certificate. Please complete that feedback form, and if you have any feedback, please mention it in that form. And after submitting that form, you will get the certificate. If you have any issue in getting the certificate, please mail us. We will give that certificate as mail. Okay. Thank you. Okay, so if you completed that feedback form, you can leave this meeting. I will wait here. So you can, after completing the feedback form, you can leave the meeting. The others can stay here and you can complete the form. Okay, I will be here. So after some time only, I will close this meeting. So you can have your time for completing the feedback form. Okay, thank you. Thank you for attending this one. Thank you very much.